Hello, I would like to welcome you to Lecture 27 of 2FH3. We'll discuss in this lecture the concept of displacement current, and then we'll put the final formulation for Maxwell's equations, and we cover Chapter 9 from the book of Sadiku, pages 411 to 416. We have seen before during our study of magnetostatics that magnetic fields are created by current. So if you have a current flowing in a wire like this one, and then you apply Ampere's law, the integral of H dot dl is equal to the current enclosed, then the current going through the surface surrounded by this contour, which will be the current I, will be equal to the integral of H dot dl. And this current here is due to the flow of charges, flow of electrons. But the problem with Ampere's law is that if you have a circuit where you have a capacitor, inside the capacitor there is a perfect insulator. So, or we can assume that there is a perfect insulator. Then there is no flow of charges in the volume between the two electrodes of the capacitor. So if you apply Ampere's law again, but instead of using the surface surrounded by the contour as the surface of the circle shown here, you instead of take it as the surface of this paraboloid shaped surface here. So this surface will intersect with the circuit that we have inside the volume of the capacitor. In that case, there is no flow of charges inside, and the integral of H dot dl will be equal to 0, even though there is still magnetic field. So in other words, if you carry out the integral of H dot dl around this contour, you will still have magnetic field because there is a current flowing in the circuit. It's a time varying current, so H will be a time varying field, but H will not be 0. So, but when you try to say this equal to the current enclosed, and you select this surface here for calculating the current enclosed, that there is no flow of charges through this surface, then the current enclosed will be 0. So this led to a contradiction in Ampere's law. Ampere's law in the way we study it was not complete. So the way we studied it earlier was that curl H, I try to show it to you here, that curl H is equal to J. So at every point in space, the current is given by the curl of magnetic field is equal to the current. In other words, the current density creates the magnetic field. And this current density, as I explained earlier, is due to the flow of charges. So it can be one of two things: either an impressed current, it's a source, or it's equal to the conduction current, J equal to J impressed plus JC. So this J can be one of two things: either it is an impressed current, which is a source, or it is the conduction current, which is equal to sigma in. So when Maxwell came, the Scottish scientist who put everything in a rigorous form, he noticed that this Ampere's law, its current form, is not working, and he added one term to correct that. So now I gave you now more like an intuitive explanation why Ampere's law, its current form, does not work in the time varying case, especially when you have capacitors. So now let's see mathematically why it doesn't work. We have studied earlier that the curl of H is equal to J, and J, we agreed, is the current density due to the flow of charges, and it can have two parts: impressed current density or conduction current density. Now it's a mathematical identity that the divergence of the curl of any vector is equal to 0. It's a mathematical identity. So if you take the divergence of both sides, this will give you 0, implying that the divergence of J is 0. But divergence of J is not 0 unless we have steady state of current. If things are time varying, then divergence of J will not be 0. We studied earlier something called continuity equation, and in that we agreed that if you have a closed volume, and there is some charge inside, and this charge had density rho v, and there is current flowing out. There is a current flowing out from the surface. Then when the current flowing out means that the charge inside this surface, inside this volume, is decreasing, because they are actually leaving the surface. So this will tell us that if there is a divergence of the current, so the current is leaving a certain volume, then the charge inside must have a negative slope with time. It's decreasing with time. So when you multiply negative by negative, you get a positive. So a positive current flowing out from a certain point in space implies that the charge inside this small volume is decreasing with time. So this means that if things are varying with time, then divergence of J will not be zero. So this led to a contradiction in this equation as well. Now, what is the volumetric charge density? Volumetric charge density, by definition, is equal divergence of D, the electric flux density vector. And because the divergence is a derivative relative to space, x, y, and z, while this is a derivative relative to time, we can move the divergence ahead of the derivative relative to time. So we can see now that the divergence of J for the general time varying case is equal to minus the divergence of partial d partial t. And it will not be zero if everything is varying with time. So now this led Maxwell to say, okay, this equation is not complete. We must add another term. And this term here is partial d partial t. Partial d partial t is a current density. We call it the displacement current density. Remember that the units of D is coulombs per meter squared. So when you divide by time, it becomes ampere per meter squared. So it becomes a current density like J exactly. So so when there is a time variation of the fields, this is equivalent to a current flowing called displacement current, and this is really the current that's flowing inside the volume of a capacitor. The current flowing inside the volume of the capacitor is not due to movement of charges, but rather it is due to the variation of the electric field inside the volume of the capacitor. And now we can correct, this is Ampere's law, the modified Ampere's law in the differential form. We can have Ampere's law now in the integral form. The integral of H dot dl is equal to the total current enclosed. So you integrate over the surface, enclosed by this L, of J plus partial d partial t dot ds. J dot ds will give us the current flow due to the actual flow of charges, and the integral over the surface of partial d partial t dot ds will give us the displacement current flow in amperes. So now this is very interesting, because now we could see that if the electric field is varying with respect to time, this will give rise to a magnetic field. J does not have to be present in the space, in every point in the space. If J even is zero, but partial d partial t is zero, this means that to be a curl of H, implying there is an H. There is a magnetic field there. So this is why in the time varying case, the electric and magnetic fields are coupled together. So now we're ready to put Maxwell's equation in the final form. We talked about it in the static form, and I did give you some hints before, or some basic idea about the general form. Now we covered all these laws. The first one is Gauss' law for electrostatics, which is the first Maxwell law. The total flux of the total electric flux from a closed surface is equal to the charge enclosed within that surface, and the charge enclosed is equal to the integral over the volume V enclosed by that surface of the volumetric charge density d volume. The second one is what we call Gauss' law for magnetic fields. The total flux of the magnetic field from a closed surface is equal to zero, because as we agreed earlier, magnetic field lines are not being generated by magnetic charges. The flux of they are simply closed lines. So what's coming into a volume will leave that volume. So you can see here in something like this, the flux in is equal to the flux out. Then the total flux through the surface must be equal to zero. The third one is Faraday's law. Faraday's law is simply saying that if you take the integral of E dot dl around the closed contour, so you are getting really an electromotive force, this will be in volts, this equal to negative the rate of change of B dot ds over that surface. And B dot ds is the flux linkage. Of course, if we have more than one turn in that surface, this will give you the flux linkage. If we have one turn, this will be psi, which is the flux. So now we know that if you have time variation of the magnetic field, gives rise to electric field. The last one is the modified Ampere's law. is simply saying if you take the integral of h dot dl around a closed contour, this will give you the current enclosed. And the current enclosed has two parts. The first part is the current due to the actual flow of charges, which is J dot ds, and remember J has two parts, impressed current and conduction current. The conduction current is equal to sigma E. Impressed current is a source, like the one you get from an antenna. Now the second part is the displacement current, and displacement current is nothing but the integration over the surface S of partial d partial t dot ds. Now this is called the integral form of Maxwell equations. We can put them in differential form, and we did cover this as well. At every point in space, the divergence of D is equal to the volumetric charge density. This is Gauss' law of for electric fields in point form or in differential form. If you apply the divergence theorem for this one, you get this expression that at every point in space divergence of B is equal to 0. This is simply saying that every point in space there is nothing called magnetic charges. Magnetic field lines they cannot diverge from any point. They are simply closed lines. If you take this one, put an integral form, if you apply here Stokes theorem, you replace this one by the integral over the closed surface of curl E dot ds and you equate both sides, you get that curl E is equal to minus partial B partial T, which is simply saying at every point in space, if the magnetic field is changing with time, this gives rise to electric field. The last one is Ampere's modified law in differential form. So if you apply again Stokes theorem, you convert this line integral to a surface integral, so it will be curl H dot ds, and you equate both sides, you get that curl of H is equal to J plus partial D partial T. So there are two ways to create a magnetic field, either due to a current flowing or due to the rate of change of the electric field. So if the electric field is changing with time, it creates magnetic field. So this is very interesting. Now we can see the electric and magnetic field are coupled together. These are all partial differential equations. You get derivatives here relative to x, y, and z. Here derivatives relative to x, y, and z. You have to equate the x component here to the x component here, y here to the y here, z to the z, and so on. You do exactly the same here. In order to get a unique solution for these problems, you need boundary conditions. So now we have to as well define the boundary conditions. We did in this course already cover the large number of boundary conditions. The first one is the continuity of the tangential component of the electric field. We said if you have any interface between two materials of different epsilon, different permittivity, the tangential electric field will be continuous. Remember, when you take the cross product with the normal, then you are getting the tangential component, because the cross product will give you sine theta, while the normal component is the cosine theta. Now the second equation that we covered already, we said that the diff, if there is no surface current, then the tangential component of the vector H is continuous between two types of material of different mu. But if there is a surface current, then there will be some discontinuity, and we did draw that. So if there is a current flowing here into the page, then I can say that the two tangential field components flowing in this direction will be different just when you cross the boundary from one medium to another, and the amount of discontinuity is equal to the vector k, and this n here is pointing from medium 1 to medium 2. This is the unit vector pointing from medium 1 to medium 2. This is the second boundary condition. So we have two boundary conditions applying to the tangential components of E and H. Now, there is one boundary condition we talked about relative to the vector D. We said that if there is no surface charge, the normal component of the vector D is continuous. So if you have an interface, this is D1 normal, this is D2 normal, they are going to be exactly the same if there is no surface charge. If there is a surface charge, then they are going to be different. In that case, D2 normal will be equal to D1 normal plus the surface charge density. The same thing is happening here for B. B is always, normal component of B is always continuous. So if you have two media, this one has mu1, this has mu2. If you know the normal component of B here, the normal component of B here, this is B1 normal, this is B2 normal. These two must be equal. So when you cross the boundary from here to here, the same value must see the same value. So we have to use these boundary conditions when we solve all type of problems. The last thing we have to remember is the constitutive relationship. B and the H are not independent. They are related by mu, permittivity, and the permeability. And permeability is equal to mu naught mu R. D and the E are not independent. They are related by epsilon. Of course, I'm talking about the linear case, the linear non-dispersive case. And the epsilon here is the permittivity, and the permittivity is equal to epsilon naught epsilon R. There is a conduction current. Conduction current is equal to sigma multiplied by E. So you can see, in order to define a medium, in the case we are discussing the simple case, isotropic case, linear case, you have to give at every point in space the conductivity, the permittivity, and permeability. These are the three parameters that define the medium we're talking about. Now let's take a look at an example. We have here an electric field. It's given by E naught cosine omega t minus omega over c z ay. E naught is the amplitude. It can be 5, 4, 3. Omega is what we call the angular frequency, and c is the velocity. You will see later when we talk about waves why we call this one the velocity. But omega is a constant, and omega over c is a constant. Actually, the term omega over c, usually they give it the term beta. It's called propagation constant in the z direction. So anyway, so this is how it's being formulated. All these are constants. The only parameters are t and z, and this field is in the y direction. So you can see it's a field component. It has only one component, which is the y component, but it's a function of t and z. It's a function of time and z. We would like for this time varying field to determine the corresponding magnetic field strengths in free space. So in free space means use epsilon equal to epsilon naught, use mu equal to mu naught, use sigma equal to 0. So now we have Maxwell's equations. We can use them to try to recover the magnetic field. First, when we draw, I would like to show you snapshots of this expression E naught cosine omega t minus beta z. First, when t is equal to 0, you get cosine beta z. Cosine beta z is simply a cosine. It at time 0 is equal to E naught, and then at later z it goes to 0 and so on. This is a snapshot, so time t is fixed. I'm just taking a snapshot with a camera for the wave. Now, if t becomes pi over 2 omega, this means there is a phase shift inside the cosine. The cosine expression will now become cosine of pi over 2 minus omega over c multiplied by z. So the whole wave will shift it to the right. It will shift by certain shift. So you can see as time goes by, this wave actually keeps on traveling. At a later time, I can draw it for you. It will maybe it will look something like this. At a later time, it will look something like this, and so on. So it is really traveling in this direction. It's traveling in the positive z direction, and this is how we get signals on our cell phones, because the waves excited by the antennas are actually traveling waves. They are propagating as time goes by. They keep on moving in the direction of propagation. Now we'll talk more about waves. Now how do we get to recover H? The one to use to go to is really Maxwell equation. Curl E is equal to minus partial B partial T. E has only one component, EY, and this EY is a function of Z and T. Anyway, I wrote for you the complete expression for the curl, and this equal to minus partial B partial T. And remember, partial B partial T has three components: partial BX partial T in the X direction, partial BY partial T in the Y direction, partial BZ partial T in the Z direction. Of course, this one will give you 0. There is no BZ, there is no EX, there is no EZ, there is no EX. And the EY is only a function of Z. So this is the only term that will remain. You get minus partial EY partial Z in the X direction. And because it's in the X direction, the only term that is non-zero here is partial BX partial T. So we equate both sides. In the right-hand side, we have only one X component. In the right-hand side, we have minus partial B partial T, and I replaced B by mu H. So B is equal to mu H, and mu here is equal to mu naught, but I left it as mu. Now, so only the X component of H will remain. The H and Y, the HY and the HZ components are zeros. With the constant fields do not propagate in the case of time varying in the time varying case. So we simply ignore them. So when you get partial hy partial t is equal to 0, means hy is a constant. It's a static case. But here we are solving for the time varying case. So here, if you could see, we know what is ey is given, so we can differentiate it relative to z. Okay, so we differentiate it to z. The derivative of the cosine will give us minus sine, and then you multiply by omega over c. So omega over c will appear out with a negative sign. So the minus will cancel with the minus. So this means that partial hx partial t is equal to 1 over mu multiplied by partial ey partial z, and this is partial ey partial z. Now, in order to recover hx, you have to integrate relative to time. So when you integrate sine omega t minus omega z over c relative to time, again you are dividing again by omega, so this omega will disappear, and the integration of sine will give you minus cosine. So you end up with this one plus a constant. And a constant here represents a static field. And as you will note, because you are using derivatives in both cases, in the time varying cases, the static field does not give rise to a corresponding electric or magnetic field. So when we are dealing with a time varying case, we set these constants to be equal to 0, because we need the time varying component only of the field. So in this case, you can see the magnetic field has a cosine dependence as well. It's a function of time and z. It's in the x direction. This is its amplitude, minus E naught over omega c. So if we put everything together, the magnetic field will be in the minus x direction. The electric field is given, it is in the y direction. Notice that the wave is propagating in the z direction. So these two are normal to one another. H and E are normal to one another, a normal direction of propagation. Which is really a common characteristic of waves, as we'll be talking about them more in a later lecture.